In this video, we're going to talk about properties of powers in a formal way. First, let's review what is the definition of powers. Powers are usually written as a to the power n. We're going to focus ourselves for n as a positive integer, meaning that n equals 1, 2, 3, 4, and so on. For a to the power n, this is really defined as a times a times a, n such a's multiplied together. So in here, n is the exponent, which here we're limiting it to be a positive integer. A is the base. So in this video, we're going to talk about operations of powers with itself, operations of powers, and powers divided by powers, so on. So let's first look at a simple example. Let's say, what is 2 to the power 10 times 2 to the power, let's say 8? What this is? One way to do it, you just multiply everything together. This is 2 times 2 times 2 times 2. 10 2's multiplied together is 2 to the power 10. And then times 2 to the 8, which is 8 2's multiplied together. Okay, but if you look at the whole thing, this is really 18 2's multiplied together. Right, there are 10 2's multiplied together, 8 2's multiplied together, and they are multiplied together. So it's 18 2's multiplied together. And this is, of course, the definition a to the power 18. And this really can be generalized into any a instead of just 2. So if I look at a to the power m times a to the power n, this is going to be equal a times a m such a's times a n such a's, and this is equals a times a, how many a's multiplied together? M plus n a's multiplied together. This is a to the power m plus n by definition of powers, because m plus n a's multiplied together is really a to the power m plus n. So here we have law number 1, a to the power a to the power m times a to the power n equals a to the power m plus n. Okay? This is law number 1. Okay? How about a to the power m divided by a to the power n? This, of course, can be write as a times a, m such a's multiplied together, divided by a times a, n such a's multiplied together. Now this relationship is divide. A, m a's multiplied together, divided by n a's multiplied together. Now let's think about a simple case when m is bigger than n. In this case, you have m a's multiplied together, divided by n a's multiplied together. So you can think about, if I write as a fraction, you have m a's in here, and then you have n a's in here. This is NA, this is MA. So you're going to cancel NA's from the numerator and denominator the same time. That makes the value keep the same, right? So in here, you're going to cancel. If I write this as separate, this is NA, and this is M minus NA, because totally there are M A's, and this is A times A, N such A's. And all those things will get canceled from the numerator and denominator at the same time. So that equals A times A, M minus N A's multiplied together. This is equals A, M minus N. Different way, actually just using a simple way to write it. Law number 2, or rule number 2 is AM divided by A to the power N equals A to the power M minus N. This, of course, we only show that for M bigger than or equal to N. This is true. But indeed, when N is bigger than M, this whole operation kind of changed from numerator and denominator, because now the denominator will have more A's than the numerator. So you're going to cancel all those A's from the numerator and from the denominator, and you're going to cancel all the A's in the numerator from the denominator, and left with just N minus M A's. And that will give you, if M is less than N, then this whole thing will equals 1A over N minus M, and that's going to be the same as A to the N minus N as well. So this formula is going to be true no matter is M bigger than N or M less than N. Okay, this is law number 2. How about look at powers of powers? Let's look at A to the power M to the power N. What this equals to? Again, we're going to use the definitions of A to the power M to the power N. This is really equal A to the power M times A to the power M times A to the power N, and such terms multiplied together. Agree with that? That's really the definition of anything to the power N really equals that thing times that thing and such things multiplied together. But now for A to the power N, M itself is really defined as A times A times A, M such A's multiplied together. Similarly go this one times A, M such A's multiplied together, and so on. The last one is A times A, M such A's multiplied together. And this, let's put a parenthesis to differentiate. This is correspond to this term, this corresponds to this term, and this corresponds to this term. And overall, there are such and such kind of parentheses there. But this, if you count the total number of A's multiplied together, is really A times A. How many A's now? Is actually M times N such A's there. So this thing, according to the definition of power, this is A to the power M times N. So this is law number 3. A to the power M times the power N equals A to the power M times N. Okay, this law is a bit of this law needs a bit of explanation. Actually, let's using an example to illustrate it. Let's make A equals, let's say 2, M equals 10, N equals 2. So 2 to the power 10, and then square it, is going to be equal to 2 to the power 20. This is example 1. How about example 2? A equals 2, M equals 2, N equals 10. This also equal 2 to the power 2 to the power 10. This is also going to equal 2 to the power 20. Okay? But this is different from A to the power M. This is a bit different because in this, the operation will calculate this m to the n first, and then you do this a to the power m and n. So just be careful that when you need a parentheses, you have to put it there, because that change the order of operations. Now let's look at another law in powers. This involves this form, a to the power m times b to the power m. Okay, don't confuse with the previous example, a to the power m times a to the power n. In here, the base is the same, that they are both a, and the powers are different. In this case, remember that this means that the ma multiplied together and na multiplied together, this equals a to the power m plus n. When the base are the same, you add in the exponent. But in here, you have base are different, the exponents are the same. Now let's look at C. Let's look at how this going to be. Again, a to the power m equals a times a. There are m a's multiplied together. And for b to the m is again the same, b times b, m b's multiplied together. Remember that for multiplications, you can change the order due to the property of commutative law for multiplication. This you can change the order of b and kind of plug the b into next to the a's, making pairs of a times b times a times b. Because there are MAs and MBs, you can pair them together to make M pairs of A times B. And this is, of course, the definition of A times B to the power M. Okay, law number 4. When base are different, the exponents are the same, then you can combine the bases together by multiplication, and then the power stay the same. So for example, let's look at a simple way of calculating 2 to the power 10 times 5 to the power 10. Now one way, of course, you can calculate this thing as 1024, and this thing I don't even know what this is, but you can calculate it and then you multiply them together. But the other way is just using this properties of that when the powers are the same, the base are different, you can just multiply them together. 2 times 5 to the power 10. Now you see why we want to do that, because 2 times 5 is just 10, so this equals 10 to the power 10, which is, of course, that equal 10 billion. So 1 followed by 10 zeros. And that's pretty cool. What if that I have the following example, 2 to the power 12 times 5 to the power 10. Now in here you have the base are different, the powers are different. What can you do now? Well, the common trick is making the powers the same. And 2 to the power 12 equals 2 to the square times 2 to the power 10 times 5 to the power 10. So you're kind of pulling some numbers out, some powers out from the bigger power. So 2 to the power 12 separate into 2 to the power 2 times 2 to the power 10. Now you do this one as in the previous example. This one equals 4 times 1 billion. Okay, so that's another common trick you can use. Finally, we're going to ask the following question. What is this value, a to the power 0? What this equals to? If you think about the definition, that means there are 0 a's multiplied together. So some students would say this probably should equal 0, right? No. You see that this does not satisfy the properties we have so far. So for example, if you do a to the power m divided by a to the power m, we know that when we divide these things, this equals a to the power, take a difference, a to the power m minus m. This is a to the power 0. At the same time, when you have a to the power m divided by a to the power m, there's the same thing this number am divided by itself, this should be equal 1. So in here, really just for consistency reason, a to the power 0 equals 1. And this fact, more of a convenience for consistency in deriving all those properties that you're going to remember this. A to the power 0 equals 1. In particular, you have this really, really weird thing. 0 to the power 0 equals 1. And don't be too surprised, because this is really does not have too much of mathematical significance. You can just treat as this is just a definition. 0 to the power 0 equals 1. And that's the end of this lecture.